Uh, Good evening, everyone. My name is Harini. Good evening, everyone. My name is Harini. I'm a PhD student from Interdisciplinary Center for Water Research at IASC Bangalore. So currently, I'm doing a PMRF TA for the course Watershed Hydrology, which is offered by Professor Rajendra Prasad sir, from IIT Kharagpur. So in this week, we will be discussing about hydrographs and how to construct flood hydrographs from unit hydrographs and what is the concept of unit hydrograph and how to separate base flow from flood hydrograph to get direct runoff. So we will be discussing these topics in today's lecture. So first, let's start with what is hydrograph. So hydrograph is the graphical representation of variations of discharge or stage with respect to time. So we have seen that. So, so hydrograph. So hydrograph is the graphical representation of variations in discharge or stage with time. We have seen the hydrographs before as well. So in previous lectures, we have talked about hydrographs, which is the graph between rainfall intensity and the time. So now we will be talking about hydrographs. So generally, the figure shown here is a is an example of a hydrograph. You can see that for if we have a isolated single storm, then the hydrograph will be single peak and right skewed. Okay. What does right skewed means? More graph is on the right hand side. So you can see that this graph doesn't look like a normal distribution. That it means it's not equal on both sides of this peak, right? So on the right side, it is extended more. This is called as right skewed. Okay. So generally for isolated higher storms, the hydrographs will be single peak and right skewed. And in case of for complex storms, so complex storms means like if suppose we have a rainfall intensity of 2 mm per hour in one single hour, and then in the second hour we have 3 mm of rainfall per hour as intensity. So like that, if we have multiple intensity of rainfall in different duration, that is called as multiple storms, like complex storm. Example for that. And in that case, we see multiple peaks. Like the hydrograph will be, might be like this. Okay. Discharge versus time. So hydrograph is also called as flood hydrograph. These are the other names for hydrographs or storm hydrograph. And where are these useful? So generally when we are designing any hydraulic structure, we need to understand the dynamics of river system. For that, we will be using a hydrograph because we will know when the peak will occur and how much will be the peak for a particular intensity of rainfall. All this information you will get from a hydrograph. So this will be helpful in designing hydraulic structures and also understanding the dynamics of river systems. So now Now we have what are the components of hydrograph? As you can see that the hydrograph is not a single straight line. It is a curve. So we can see it's rising initially and then it is peaking at some point and then it is falling down. So that's how we divided the hydrograph into three parts. Like we are saying, we have a rising limb, we have a crest, and we have a recession limb. So what are the characteristics of rising limb is it is also called as concentration curve. That means whatever the discharge is getting concentrated at the outlet. Okay, it is reaching from different parts of the catchment and it is getting concentrated at the outlet or any station where we are trying to create the uh, hydrograph. And then we can also see that it reflects increase in discharge from catchment. So this also gives us an idea of storage that is built due to overland flow and also channel phases. Okay. And we can see that this rising limb will be always a function of storm characteristics only because it depends on the intensity or the duration for how long the storm has occurred. Based on that, the rising will be the slope of the rising and also the amount it will rise. It will all depend on the intensity, duration of the storm. So it doesn't depend on the basin characteristics. So in case of crust segment, we can see that the point C and D, the curve joining C and D is called as crust segment. This is because at point D and C, we observed a drastic change in the slope. Suppose the slope here is M1, the slope will change drastically, which will be M2 here. Similarly, at point D also, we will observe a drastic change in slope. These points are called as point of inflection, C and D. Okay, where we observe change in slope. The curve C and D represents the crust segment. Okay, where peak discharge is included. And the crust segment will be a function of both storm characteristics and basin characteristics. Why is it? Because in case of suppose if you take same intensity of rainfall that is occurring, in case of urbanized areas, we will see that most of the rainfall will be converted into a runoff because there won't be any infiltration that is occurring due to urbanization. Okay, so we will observe high peak, but in case of forest areas, there will be lot of losses due to interception and also due to infiltration. So the peak will reduce because of the losses. So that's why the crust segment will always be a function of the storm characteristics as well as the basin characteristics. Also, now coming to the third component of hydrograph, that is recession limb. So recession limb is always a function of basin characteristics. This is because in recession limb, the water that is coming into the river is mainly due to the natural groundwater flow. So, natural groundwater flow at the recession limb. So, when you see here, so based on the land use land cover characteristics of the basin, the recession limb will be characterized. Suppose if it is a forest area, we can see that a lot of water will be infiltrated into the soil, and this will slowly flow as interflow, and also some of the burst flow will finally contribute the channel flow. But in case of urbanized area, this recession limb will be shorter. I mean the duration of the recession limb. So that's how we say that rising rim is a characteristic of storm characters, and the crest segment is a function of both storm and basin characteristics. And in case of recession limb, it is a function of basin characteristics. Okay, now coming to the key elements of hydrographs. So in this figure, you can see that we have discussed the three components: rising limb, crest, and recession limb. But also you can see some variables like TP, TB, and all. So these are the key elements of the hydrograph. So the first key element is storm or rainfall duration. So the storm or rainfall duration is the duration of the excess rainfall represented by hydrograph. So it is represented by TR in the figure. Okay. So it is the excess rainfall excess duration represented by hydrograph. Okay. So so in this case, we have seen that this is our hydrograph, and generally we will represent excess rainfall hydrograph here in blocks as we have discussed. So this x-axis represents the time and y-axis is the rainfall intensity, right? So the duration of the excess rainfall, TR, is the storm duration or rainfall duration. And the other characteristics of other key elements of hydrograph are time lag or basin lag. So as you can see that here, this time difference is the time interval is the time lag. That is the time interval from the center of mass of excess rainfall to center of mass of runoff hydrograph. So here, since it's a single block, the center of mass of this hydrograph will be the midpoint of the hydrograph, and generally the centroid of the hydrograph might lie near the peak or closer to the peak. Okay, so suppose this is the center of mass of the hydrograph. The time difference between these 2 points is called as time lag or basin lag. Okay, so the next element is time to peak. So here it's represented by TP. As we can see that time to peak is the time interval for the hydrograph to reach the peak from the start. Okay. So it is the time interval between start of hydrograph to the peak. This is called as time to peak. As the name itself suggests, like what is the time it takes to reach the peak is called as time to peak. Next we have time base, TB. So it represents the time interval from beginning of the hydrograph to the end of the hydrograph. That is like total time the runoff will be observed due to a storm event is called as time base. Okay. So it's the time interval from beginning of resulting hydrograph to the end of that hydrograph. This is called as time base. Okay. And the next key element is the peak discharge. QP. So here we can see that in the hydrograph, since it's a single storm or like isolated storm, we can see there is only one single peak. So whatever the discharge that corresponded to the highest discharge is called as peak discharge. Okay. In our case, the point P represents the peak discharge. So now let's see what are the factors that affect hydrograph. So in previous class, we have discussed about the factors that affect runoff, right? So whatever runoff that is coming at a station or the outlet is what we are plotting in hydrograph. So same factors which affects the runoff will be the factors that affect the hydrograph as well. So the first one is we have discussed, sorry, meteorological factors. Okay. So in this meteorological factors, we have discussed about the rainfall intensity, the amount of rainfall, okay, rainfall intensity and pattern. Okay, what is the size and duration of storm event. Okay, and we have also talked about aerial distribution. For large area basins, we can see high amount of runoff occurring compared to smaller basins. Okay. Also, we have seen about the direction, how direction of storm movement will affect. So if the direction is, suppose we are trying to get hydrograph at this point, if the direction is downward of the storm, then we observe higher peak than when the storm moment is upward. Okay. Here you can see in this figure. So we have discussed about physiographic factors like size and shape of basin, the drainage type, whether it is urbanized or uh, forest cover based on that, and then slope of land surface, So, as we can see that in this third figure, if the slope is more, if it is more steep, then you can see that the discharge will be peak. You can observe a peak discharge more than compared to a mild slope surface, and it depends on storage detention of watershed. So how much water the watershed can store. That also affects the runoff, right? So obviously it will affect the hydrograph. And in the case of drainage type, we have seen how fan shaped and funnel shaped hydro catchments will show the hydrograph, like, right? So the third factor is human factors. This is we have already discussed how urbanization will affect the hydrograph. You can see peak flow, and also the time to peak will be less compared to a forest or other land surface. And also how plowing will affect, and the drainages that we are constructing, also afforestation, basically how the land use cover change will affect the runoff. That will in turn affect the hydrograph that we are constructing from the runoff. And cropping factor, all these are the factors that affect our hydrograph. So generally, as we have seen that we have talked about hydrograph, which is also called as flood hydrograph and base storm hydrograph, we can see that there is always some flow that is occurring. Suppose in case of perennial rivers, we have discussed that there will be some kind of flow that will always occur, right? That is mostly due to the contribution from the base flow. So when a storm, when an excess rainfall event has occurred or a storm event has occurred, some part of the rainfall will be stored will go into the soil as infiltration. We have discussed earlier, and this infiltration will slowly reach the rivers as interflow or base flow, right? So generally, base flow will take a longer period compared to an interflow. So we say that even though if there is no storm, suppose storm is starting at this point A, we see that slowly the peak will be coming. But before that also there is some flow. This is due to the water that is coming from the groundwater, that is the base flow. Okay. So generally what we are interested in is mostly the direct runoff because we want to isolate the base flow component of the hydrograph. So in this base flow separation, what we are trying to do is we try to distinguish and isolate the base flow component from the total runoff. So as we have discussed, the precipitation infiltrated into soil is subsequently discharged into rivers. Okay, this is what is the base flow. So it provides why are we doing the base flow separation is that it is this is we need to understand the base flow value because it will provide a continuous and steady flow between precipitation events. Okay. which is crucial for stream flow during dry periods. Suppose during dry periods, when there is no rainfall event, this might be the only source of water for for day-to-day purpose or any for drinking and etc. So we need to know the base flow component also. Okay, so it provides steady, continuous flow between the rainfall events and crucial for maintaining is it not visible? I'll share my screen again. Mhm. So there might be an internet connection that I'm facing. That's why I'm not able to just share the screen once. Now is my screen visible?
Yes,
Yes,
ma'am.
yes, yes. Yes, yes. Now it's not visible.
Let me share it again. Oh, it's fine, right? Okay. So here Pawan was asking how do we estimate the time lag between the rainfall event and the base. So I don't have much idea related to that, but based on the groundwater flow. So in groundwater course, we will have some equations related to that, like Darcy's law and all. So that we will apply to generally calculate the how much time the water will take to flow from one place to another in soil. So using that, we will try to calculate the time lag that occurs between the rainfall event and the base flow. So this is what I have in my mind, but I'm not sure. Maybe I can check and come back to you in the next class. Mhm. So right now we are discussing about base flow separation and why we are trying to separate the base flow so that because it is the steady and continuous flow that will be available throughout year. So which will be mainly useful during the dry season. Okay. So it will be useful maintaining stream flow during dry periods. Okay. So once from flood hydrograph, so once if we separate the base flow from flood hydrograph, then whatever hydrograph that we are getting is called as direct runoff hydrograph. Okay. Flood hydrograph minus base flow is equal will give us minus base flow will give us direct runoff hydrograph. Okay. As you can see here, this total hydrograph is the flood hydrograph, and we have, suppose we have a base flow, and this line is separating the base flow component. So the above the hydrograph above this base flow line is called as direct runoff hydrograph. Okay. So we have different methods. How we will estimate, how we will separate this base flow. Okay. So the first method is the straight line method. So in this straight line method, what we will do is we will join the uh, start of the rising limb point, that is A, and the end of the recession limb, that is D. Suppose this is the start of rising limb and point A, and D is the end of the recession limb, that is point 2, point D. The line joining these two will give us the uh, volume of base flow. So this area will give us the base flow volume. Okay. So from first what we will do is that we know these 2 points A and D, and from that we will estimate the slope value. And using the slope, we will calculate the ordinates of the base flow. And then just simply by subtracting the flood hydrograph value by subtracting the base flow values from flood hydrograph, we will get direct runoff hydrograph. So, and I hope the first method is clear. The second method is, there is some issue with my pencil also. Sorry for that. So the second method is, so I'll just say it. So the second method is fixed base length or concave method. So what we will do is, instead of simply drawing a straight line joining the starting point and the end point of the hydrograph, what we will do is first we'll draw a vertical line at the peak. So this is the vertical line. Okay. So this is our vertical line. We'll first draw this line. And at point A, that is the start of the hydrograph, we will just draw a tangential line. Okay. AF. And then we will calculate this n values. Okay. This n is calculated using a formula n equal to n equal to 0.827 into a power 0.2. So A is the catchment area in kilometer square. Okay. This is fixed base length method or concave method. Okay, so once we get the n value, number of number of days from the peak is estimated using this n value, and we will have a point S from that. Okay, and we will join the points S and F. Okay, and then we will get one more line. So we will say that the area below this curve AFS is the base flow. Okay, it will give us base flow volume, and the area above this, sorry, the area below AFS is the base flow volume, and the area above it will contribute to direct runoff. So, is this clear? In the straight line method, what we will do is like we will join the 2 points, the start of the hydrograph and the end of the hydrograph with a straight line. We will estimate the slope, and from the slope we can calculate these ordinate values, and we will just subtract the flood hydrograph. We'll do flood hydrograph minus base flow to get the direct runoff. And the volume below this line will give us base flow volume. And in case of fixed base length or concave method, what we'll be doing is we will first draw a vertical line at the peak, and we will draw a tangential at the point A, which is the start of hydrograph. And where this tangent intersect this vertical line will be our point F, and then we will calculate the number of days from the peak. Okay, n using this formula, which is a function of catchment area, and we will identify point S. Okay, and from F we will draw a straight line to S. So the area below this line below this curve AFS will give us the base flow volume, and above it will be the direct runoff component. So also we have two more methods, that is variable slope method. So variable slope method and also constant slope or area method. Okay. So in the case of variable slope method, as we have discussed previously, we will first draw the vertical line at peak flow here. And then what we will do is we will draw a tangent at the start of the hydrograph, and we will find the point F where this tangent will intersect this vertical line. And then what we will do is that we will draw one more tangent at the end of the hydrograph point. That is at point D, we will draw a tangent, and we will extend it till it intersects the vertical line at the point of intersection, point of inflection I. Okay, we will draw a vertical line at point I, which is the point of inflection, and where this D point will meet this G. So sorry, where this tangent will meet this vertical line is given the name G, and the area under AFGD will contribute to the base flow volume, and the area above will be the direct runoff volume. Okay, so the third method is variable slope method, and the fourth one is constant slope or area method. Like in the fixed base method, what we will do is like we will calculate the number of days from from the peak using the formula n equal to 0.827 into a power 0.2, where e is in kilometer square, and we will get number of days. Okay, so this we will use to locate the point S from the peak, and we already know E is the start of the hydrograph, and we will just draw a straight line joining A and S. Okay, so the area below the line AS will be the base flow volume, and the area above will be contributing to direct runoff. So the two methods that we discussed to how to separate base flow Is this clear? First one is the straight line method. Second one, fixed base, variable slope method, and also we have discussed constant slope method. If you guys have any questions, you can ask me in this part. So, if there are no questions, I'll just go for some problems related to that, problems and questions. So the first question is, for a complex storm event, the hydrograph will have single peak right skewed. Option A. Option B is single peak left skewed. Option C is it will have multiple peaks. Option D is none. Any answers? So the answer is in a complex storm, we will have multiple rainfall events. So there we can see that a hydrograph will also have multiple peaks because of multiple rainfall events. Okay, and second question is, using which parameters hydrographs are constructed? Option E, stream discharge versus time. Option B, time versus area. Option C, discharge versus time. Option D, stream discharge versus area. So as we have discussed, hydrograph is a plot between time and discharge or stage. Okay, so that means the option is A, stream discharge versus area. So here in third question, the shape of rising limb of the hydrograph depends on option A, basin as well as storm event. Option B, storm characteristics only. Option C is basin characteristics only. Option D is baseflow only. So in case of rising limb of a hydrograph, we have seen that it will mainly depend on the storm characteristics based on the intensity, duration, and different characteristics of storm. The slope of the rising rim and the height to which it rises, everything will depend on the storm characteristics only. So the next question is, the shape of recession limb of a hydrograph depends on option A, basin as well as storm characteristics. Option B, storm characteristics only. Option C, basin characteristics only. Option D, base flow only. So as we have seen that in the case of the hydrograph, the recession limb mainly depends on the basin characteristics, because in case of urbanized area, we have seen, as we have already discussed, that the this duration of the recession limb will be shorter, because most of the water will get directly reach the river. But in case of like forest areas or anything, we will see that it will first get infiltrated, and then from the soil the water will reach the river, right? So it will take some time. That's why the shape of recession limb will mainly depend on basin characteristics. So the next question is, the point of a hydrograph which represents the maximum amount of water that can be stored in the catchment is termed as. So in case of hydrograph, when we are drawing, we have talked about the start of the hydrograph to a point of inflection as the recession limb. And this will give us the details about the water that can be stored in the catchment. So that means the maximum amount of water that can be stored in a catchment, which point will represent mainly the point B, that is point of inflection. Okay, so the next question is, the lag time of a basin is the interval of time between the centroid of rainfall and dash of the rainfall. So when we have plotted the hydrograph, we have seen that, suppose this is the rainfall intensity, sorry, excess rainfall hydrograph, the centroid of this and the centroid of the hydrograph, this this time interval is called as time lag. Okay, so since from all these options, most appropriate option is the peak because the center of the hydrograph will mostly near to the peak. So that's why we can say that we can go with the option peak. So next question, which of the following are the factors that affect hydrograph? So option A, rainfall intensity and pattern. Option B, size and shape of the basin. Option C is urbanization. Option D is all of the above. So as we have seen that all the factors that affect runoff will be the factors that affect hydrograph because hydrograph is a plot between discharge versus time, right? So we have seen also we have discussed in today's class also that rainfall intensity and pattern will affect the hydrograph. Also size and shape of the basin, urbanization, all these factors affect the hydrograph. So the option is all of the above. So the next question is a hydrograph is a graphical representation of option A rainfall intensity versus time. Option B is rainfall depth versus time. Option C is discharge versus time. Option D is cumulative rainfall versus time. So we have discussed in rainfall uh, lecture that hydrograph is a box plots between rainfall intensity and time. So the option will be option A, rainfall intensity versus time. So the next question is area under effective rainfall hydrograph is equal to. So the rainfall hydrograph, how do we calculate? Suppose we have a hydrograph. That means total precipitation intensity versus time. Okay, rainfall intensity versus time is the hydrograph. What does effective rainfall hydrograph mean? Suppose if we have pi index over here, we'll draw the pi index and then this will be our excess rainfall hydrograph. So the area under excess rainfall hydrograph, that is whatever the rainfall after infiltration and initial abstractions, whatever the rainfall is left will always contribute to the runoff, right? So the area under effective rainfall hydrograph will be equal to direct runoff volume. But if you can see that here the rainfall intensity is in mm per hour, suppose if we take, and time is in hour, then if in when we calculate area, the units will be in mm. So if we see the options, the option A is direct runoff volume in mm. Option B is direct runoff volume in mm cube. Option C is total rainfall in mm. Option D is none. So as I have told now, the area under excess rainfall will be the volume that will be coming out as direct runoffs, but the units of it will be in mm. Okay. So now let's discuss about what is effective rainfall hydrograph and direct runoff hydrograph. So here, in case of effective rainfall hydrograph, as we have told that from the total rainfall hydrograph, we'll first remove the loss terms by using pi index or W index. We will remove the losses. Okay, and then whatever rainfall that we call as excess rainfall. Okay, so then what we will do is that this area under this excess rainfall will be the direct runoff volume. Okay. So in this what we will do is like from rainfall we will subtract initial and infiltration losses. Then we will get effective rainfall hydrograph. That we will do using pi index or W index. And the area under effective rainfall hydrograph will be the direct runoff volume. So, what is direct runoff hydrograph? As I have told before, from the flood hydrograph, if we remove this base flow component, then whatever the hydrograph, the resulting hydrograph is called as direct runoff hydrograph because uh, this base flow is due to both the precipitation and precipitation which will get infiltrated, and then from the groundwater the flow will be contributing to the runoff, right? So if once we remove that component, whatever runoff that is left is called as direct runoff. So generally DRH is direct runoff hydrograph will be developed by flood hydrograph minus base flow. And suppose area of excess rainfall hydrograph is in mm, right? So if you multiply with area of catchment, it will give us direct runoff volume. That is equal to area under direct runoff hydrograph. Is this clear? So if you calculate area under direct runoff hydrograph, that will give us the direct runoff volume because discharge units are meter cube per second and we have time, right? Once we calculate area, the units will be in meter cube. So area under direct runoff hydrograph will give us direct runoff volume. So also we have seen that area under excess rainfall hydrograph will be in mm and gives us direct runoff volume in mm. Right. So once we multiply with catchment area, it will be in terms of volume, that is meter cube or cube, depends. So this is how we form a relation between excess rainfall hydrograph and direct runoff hydrograph. Okay. So now we will look into the concept called a unit hydrograph, sorry, which is given by Sherman in 1932. So, unit hydrograph is the direct runoff hydrograph generated due to 1 unit depth of excess rainfall that has occurred uniformly over the basin and at a uniform rate and for a specified duration of d hours. Okay. Mhm. So, how is unit hydrograph defined? Is unit hydrograph is the hydrograph of direct runoff generated due to 1 unit depth. So it can be 1 centimeter or 1 mm or 1 inch. Okay. 1 unit depth of excess rainfall. Okay. Remember this term excess rainfall. It is not total rainfall. Should be excess rainfall. That is like from total rainfall, you have to subtract the initial losses and infiltration losses. Okay. And this excess rainfall should be occurring uniformly over the basin. And at a uniform rate for a specified duration, the hours. Okay. Suppose if you see here in this, we can see the height of the hydrograph is 1 centimeter per hour. Okay. So we have 1 centimeter of excess rainfall. Sorry, here it is the 1 centimeter of excess rainfall. The height of it is given, and the duration is 4 hours. That means for 4 hour duration, we have a unit hydrograph. That is like 1 centimeter of rainfall has occurred for 4 hours. What will be the hydrograph that is generated? That is our 4 hour unit hydrograph. Hmm. So here there are a lot of assumptions when you are constructing a hydrograph. As you can see in the definition itself, we have mentioned two assumptions that the excess rainfall should be occurring uniformly over the basin, which won't be happening in mostly in the real time. So the first assumption is excess rainfall. VR is excess rainfall here, okay, is uniformly distributed within its duration. That means suppose if we are saying 1 centimeter of excess rainfall occurred in 4 hours, so it should be uniformly distributed in that 4 hour period. Okay, so that is one of the assumption. And the second assumption is excess rainfall is uniformly distributed over the whole area of catchment. And the third assumption is base time. This from the start of hydrograph to the end of hydrograph, the base, it is called as base time. Okay. The base time of DRH, direct run of hydrograph, due to excess rainfall of unit duration is constant. That means this base time base should not change with the due to the excess rainfall's unit duration. Okay, it should be constant. And the unit hydrograph, UH represents unit hydrograph, reflects the effects of various physical characteristics of basin. That means it doesn't change with time. If there is a drastic change in land use, land cover of the basin, then there you can see that the unit hydrograph also changes. So we also say that. So is this property is called a time invariance. Okay. And the last assumption is the response of drainage basin is linear. So that means it satisfies principle of proportionality and superposition principle is applicable. Okay. We'll discuss what is principle of proportionality and superposition. So let me share the screen again. So, what is principle of pro- proportionality is that if duration of excess rainfall is fixed, but its volume is changing. That is like suppose you have for 4 hour duration, we have 1 centimeter excess rainfall. Suppose you have 2 centimeter of excess rainfall. Okay, like this, the duration is fixed, but the uh, excess rainfall value is changing. So 1 centimeter, 2 centimeter, 4 centimeter, like that. Okay, if the duration of excess rainfall is fixed, principle of proportionality. If duration of excess rainfall is fixed, but its volume changes, then the duration of direct runoff hydrograph won't change, but its ordinates do in proportion to the volume of excess rainfall. So suppose we have a 4 hour, 4 centimeter, 4 hour flood hydrographs or a direct runoff hydrograph. This is our hydrograph. Okay. So for this is the direct runoff hydrograph due to 4 centimeter rainfall. So whenever hydrograph you are drawing, it should touch the x-axis at both the ends. Okay. Because we are removing the base 4 component. Right. So if this is due to 4 centimeter of excess rainfall, when you are trying to calculate a direct runoff hydrograph for 2 centimeter, how we will calculate is what they are saying is this time base will not change. Okay. This will be fixed. It will only the ordinates of the hydrograph only will change. Okay. Each ordinate of this 4 centimeter DRH will be divided by 2 because it's 4 by 2. From 4 centimeter, we are trying to get 2 centimeter DRH. Right. So we will just, what we will do is 4 by 2, that is 2. We will divide all the ordinates of 4 centimeter DRH by 2 to get the 2 centimeter DRH. So that is what principle of proportionality means. So now we'll talk about one more principle of superposition. So in case of simple principle of superposition, what it will do is it allows the decomposition of complex ERH, that is excess rainfall hydrograph, into rectangular blocks or pulses, and then superimposing on one another the hydrograph of these rectangular pulses, each of steady intensity, is used to obtain the total DRH. This definition sounds too complicated. What they are trying to say that is like, suppose here we always talked about single storm event, right? But in real case, there won't be only one single storm that will be occurring. Suppose if we see that if we have like multiple storm events, okay, suppose this is 1 centimeter, 2 centimeter, again 1 centimeter, it is occurring at 4 hour duration in each of these cases. What we have to do is we can use the principle of superposition. That is, means suppose if we have a uh, 4 hour duration uh, flood direct runoff hydrograph. Okay, 4 hour duration with 1 centimeter excess rainfall. If we have a direct runoff hydrograph, TRH of 1 centimeter. Okay, and after 4 hours, we can see that there is one more storm event occurring of 2 centimeter, and then we also have 2 centimeter for DRH. So the direct runoff hydrograph of 2 centimeter excess rainfall, which is starting at fourth hour, right? And we also have at eighth hour one more rainfall event happening, which has an excess rainfall of 1 centimeter. We have a direct runoff hydrograph for 1 centimeter excess rainfall, right? So that again will plot here. So once we add up all these ordinates, suppose at time 0, what is the ordinate? At time 1, this will be our ordinate. At time 2, this and this both are falling, right? So we will add up these two terms. And at time, this is 4th hour, 8th hour, and 12th hour, we'll add up all the ordinates that are coming in this time step, okay? So this is like superposition. This is called as superposition. So all that together, we will have a one single direct runoff hydrograph for this kind of complex storms. Okay, so that is what principle of superposition is telling us about. But there are limitations of unit hydrograph. That is like one is we have already discussed that rainfall cannot happen uniformly across over the basin and also with the time, right? So that is one of the drawback in real time. And also it can be only applicable for drainage areas that lie between 200 to 5 lakh hectares. Okay. So now coming to what are the applications of unit hydrograph? Why are we doing this? That's because unit hydrograph will be helpful in developing flood hydrograph, which can be used for designing a hydraulic structure. Suppose if we have a unit hydrograph like this, suppose for 4 hour duration, we have a unit hydrograph. Okay, suppose we know that the maximum rainfall that can occur at a particular place is 100 centimeter. So what we can do is from this unit hydrograph and by applying this principle of proportionality, uh, we can get a flood hydrograph or direct runoff hydrograph first for this 100 centimeter excess rainfall. Okay, that is just by multiplying the ordinates of the unit hydrograph with 100. Okay, once you get direct runoff hydrograph, you just add up the base flow components to get flood hydrograph. This flood hydrograph will give us what can be the peak of the peak runoff that can occur due because of this 100 centimeter excess rainfall, right? So this will be used for designing the hydraulic structures, and also it can be used for as an extension of flood flow records based on rainfall records. Suppose we don't have a record of what is the runoff that occurs for like 150 centimeter of rainfall. So using the unit hydrograph, we can generate flood hydrograph for 150 centimeter excess rainfall. And then from that, we will know what will be the peak discharge in a river due to that amount of rainfall. Okay. And it can also be useful for flood forecasting and an early warning system because we can obtain the peak of the hydrograph, right? That is the peak discharge. So now let's look into how to construct a unit hydrograph for an isolated storm. Generally, what we will do is if we have any past records, from past records, select an isolated storm, okay, which is uniformly distributed over the basin. This we have seen that it is one of the assumption of unit hydrograph, right? And then what we will do is we'll plot the storm hydrograph for this particular storm. From the records we will have generally what will be the because we can use the stream gauges to measure the runoff and discharge in the stream, and using that we can just plot a storm hydrograph for this particular isolated storm. And then what we will do is we'll get direct runoff hydrograph by using this. We will subtract from flood hydrograph, we will subtract the base flow component, right? Using any of the methods that we have discussed earlier, we can just subtract those base flow values from flood hydrograph or storm hydrograph to get direct runoff hydrograph. Then what we will do, we'll calculate what is the direct runoff volume. So generally what we will do is we'll take the area under this entire curve, right, for the direct runoff hydrograph. Uh, so for this we can generally directly use this formula 0.36 by summing up all the direct runoff hydrograph ordinates into delta t is the time gap. So here in this case it's 12-hour time gap in by area. Since the area under DRH gives us in volume, that is meter cube, we will divide by area to calculate the direct runoff in mm. Which, so here the area will be the catchment area in kilometer square. Time interval will be in hour, and direct runoff ordinates for each time step. We'll just add them up. So that's how we get a direct runoff value. So we already know this is equal to excess rainfall, right? Then what we will do to get, but we know that the unit hydrograph is for 1 centimeter excess rainfall. But if we have some 10 mm of direct runoff, what we will do by principle of proportionality, we have to divide all the ordinates of DRH by 10. Okay, then we will get the direct runoff hydrograph for 1 centimeter excess rainfall. So for unit hydro, calculate unit hydrograph ordinates, you will divide the direct runoff ordinates with this direct runoff volume. So suppose this is the direct runoff for 10 centimeter excess rainfall. Okay, we can see that how we are trying to find this 10 centimeter value is like we will just calculate the area under this direct runoff hydrograph of 10 centimeter excess rainfall, and we will just divide it by area of the catchment. Then we will get this 10 centimeter excess rainfall or direct runoff value. And then what we will do, each ordinate of this direct runoff hydrograph will be divided by this 10 to get the unit hydrograph ordinate. So then we will see about how to construction of unit hydrograph. So from flood hydrograph, so now that if we have a unit hydrograph for a particular catchment, how do we construct a flood hydrograph? So construction of flood hydrograph. So we have seen that suppose if we have a unit hydrograph for 4-hour duration, that means 1 centimeter excess rainfall and 4-hour duration. Okay, we have this as our unit hydrograph. Okay. So then what we will do, suppose if we want to calculate the flood hydrograph for, this is for 1 centimeter. for 4 centimeter, what we have to do is each ordinate of unit hydrograph will be multiplied with this direct runoff value or excess rainfall. Here in this case, it is 4 centimeter. Okay. So if we multiply each ordinate with by 4 centimeter, the time base won't change. Only the ordinates will increase. So this is our 4 centimeter direct runoff hydrograph. Then to get flood hydrograph, what we have to do is the direct runoff hydrograph plus base flow will give me the flood hydrograph values, ordinates. That means flood hydrograph ordinates is equal to direct runoff ordinates plus base flow ordinates. Sometimes, most of the cases, what we will do is for easier calculation, we will consider the base flow ordinates as constant, like that constant. Then we will just add the constant value to each of the direct runoff ordinates to get the flood hydrograph ordinates. So in the case of complex storms, what we will do is complex storms is like we have seen that we have multiple rainfall storm events that are occurring. Suppose in this case, see in one, suppose D is the hour, okay? In D hour duration, we see R1 amount of excess rainfall that is occurring. In the next D hour duration, R2 amount of excess rainfall is occurring. In the third D-hour duration, R3 amount of rainfall is occurring. So what we will do is by principle of superposition, if we know that the unit hydrograph is this, okay, like U1, U2, U3, these are the ordinates of unit hydrograph for a particular basin, that is for 1 centimeter excess rainfall and D-hour duration. Then what we will do is to develop a flood hydrograph for complex storm. First, by using principle of superposition, that is like we will add up different, we can add up different direct runoff hydrographs. To develop direct runoff hydrograph for R1 excess rainfall event, we will multiply the ordinates of unit hydrograph by R1. Okay. We'll see here you can see R1 U1, R1 U2, R1 U3. All this we are multiplying each ordinate of unit hydrograph by R1. And then we are plotting a direct runoff hydrograph. And then we see that after D hour, there is a rainfall event of R2 excess rainfall. Okay. So there will be another, we have to start the direct runoff from D hour. The next hydrograph should be started from the D hour. Okay. So here this hydrograph is obtained by multiplying each terms of unit hydrograph with R2 because R2 is the excess rainfall for this particular storm and it is starting at time D. Right. So here also we are starting this direct runoff hydrograph from time D. And similarly, we see that R3 amount of excess rainfall is starting at a time t equal to 2d. Okay. Also, then what we will do first, we'll try to calculate the direct runoff hydrograph by multiplying the ordinates of unit hydrograph with R3. And then we know that it's starting at 2d. So we will start this hydrograph at 2d time step. Okay. And then we will plot this. So then what will happen is suppose now we are trying to calculate the ordinates of flood hydrograph. So here at this step, this will be the ordinate of flood hydrograph and this will be the ordinate at time equal to 2d. And this entire length will be the ordinate of flood hydrograph at time 3d. So that means we have to sum up all these parts at each time step to get the ordinates of direct runoff hydrograph for this kind of composite storms. And once we have this, if we include the base flow term at each time step, so the base BF1 is the base flow value at time step 1, 2. If we do this, So we add all these terms, then we will have a flood hydrograph for this kind of complex storms. Okay, so that's how we do it. Is this clear? Any questions? So if there are no questions, let me proceed to some questions related to these topics. So the first question is, a unit hydrograph has 1 unit of dash. So option A is peak discharge, option B is direct runoff, option C is rainfall duration, option D is time of direct runoff. So as we have seen already, unit hydrograph is due to 1 centimeter excess rainfall occurring for d-hour duration. Okay, so this 1 centimeter is the excess rainfall. That is in turn also named as direct runoff. Right. So that means a unit hydrograph has 1 unit of direct runoff. So the next question is the use of unit hydrograph for estimating floods is generally limited to catchment of size less than option A 5,000 kilometers square, option B 500 kilometers square, option C 106 kilometers square, option D is 5,000 hectares. So as we have discussed, the area should be within 200 to 5 lakh hectares, right? So, but the answers are given in terms of kilometer square. So, 1 hectare is 100 kilometer square. So, the maximum size of the watershed can be 5 lakhs, right? So, just divide 5 lakhs by 100. Sorry, 100 hectares is 1 kilometer square. Okay. So, that means it's 5,000 kilometers square. So here the next question is 1 centimeter of excess rainfall occurs in 3-hour duration. The duration of resulting hydrograph is. So generally what we have seen is, suppose in the case of unit hydrograph, we have 1 centimeter excess rainfall occurring for 3-hour duration. So this means this we call as 3-hour unit hydrograph, right? So that means the duration of the resulting unit hydrograph will be 3 hours. So the next question is a triangular direct runoff hydrograph due to 6-hour storm in a catchment has a time base of 100 hours and a peak flow of 40 meter cube per second. The catchment area of the catchment area is 180 kilometer square. The 6-hour unit hydrograph of this catchment will have a peak of how many meter cube per second. So here they are saying there is a direct runoff hydrograph for a 6-hour storm. So it's a triangle where the time base. Since it's a direct runoff hydrograph, it should start and end with x-axis. Okay, that means zero base flow. So this is 100 hours. The time base is, and the peak discharge is 40 meter cube per second. They are saying. Okay. So they did give us excess rainfall value. So how much amount of excess rainfall is occurring for this particular DRH, they haven't given. But they have told that catchment area is 180 kilometers square. So first we need to find the excess rainfall value. So that is excess rainfall is like we first calculate the area under the DRH under DRH divided by catchment area will give us direct runoff or excess rainfall value. So that is, since it's a triangle, we can calculate the area of triangle by half base into height, half base 100. Since it's in seconds, I'm converting the time in hours, from hours to seconds. That is by multiplying 3600 into 40 by area is 180. Okay, into 10 power 6. I'm converting this into meter square. Right. Once you solve this, what we will get is 0.04 meters, that is equal to 4 centimeters. That is, this direct runoff hydrograph corresponds to 4 centimeter excess rainfall occurring at 6 hour duration. So this is 4 centimeter 6 hour. But for unit hydrograph, what we have to do is that the excess rainfall is 1 centimeter. So as we have seen in principle of proportionality, we have to divide all the ordinates of direct runoff hydrograph by 4. Okay. Because 4 by 4 is only 1, right? 1 centimeter. Barabar. 1 centimeter. Then only you will get 1 centimeter excess rainfall. So since we know that maximum discharge for 4 centimeter excess rainfall is 40 meter cube per second. So maximum discharge for 1 centimeter excess rainfall will be 40 by 4. That is 10 meter cube per second. So 1 centimeter excess rainfall means unit hydrograph. So the answer is option A. So the next question is, the lines that depict area of approximately equal time interval are known as option E isoheights, option B isobars, option C isochrones, option D is isoplinth. So isoheights is the lines that joining where same amount of precipitation is occurring. Isobar is the lines that joins the points where same amount of pressure is seen. And isochrones is the lines that join the points which have same amount of time of concentration. That is, like, it will take equal travel time from that point to a particular outlet or a station under observation. So our option will be option C. Isoplate is like the points which show same meteorological values will be joined to get a isoplate. So next question. A peak flow of flood hydrograph due to 6 hour storm is 470 meter cube per second. The corresponding rainfall depth of rainfall is, so average depth of rainfall is 8 centimeter. Assuming an infiltration loss of 0.25 centimeter per hour and a constant base flow of 15 meter cube per second is occurring, what is the peak discharge of 6 hour unit hydrograph? So here you can see, first of all, it says flood hydrograph. So to calculate direct runoff hydrograph, what we have to do is, first, flood hydrograph should be subtracted. The base flow should be subtracted from flood hydrograph. So that is, to get the peak of direct runoff hydrograph, we have to do 470 minus 50. That is 455 meter cube per second. And then here you can see, this is average depth of rainfall is 8 centimeter and infiltration loss is 0.25 centimeter. So first, we have seen that the hydrographs are developed for excess rainfall. So to calculate excess rainfall, we use pi index. That is pi equal to P minus ER by T. So here generally we will take runoff, that is direct runoff, which is equal to excess rainfall. So this implies pi is given as 0.25. The precipitation that is occurring is 8 centimeter and excess rainfall we have to calculate, and it is occurring for a duration of 6 hours. It's a 6 hour storm. So this means 8 minus ER equal to 1.5. ER is equal to 6.5 centimeters. So excess rainfall is 6.5 centimeters. So now we have what we have for 6.5 centimeter excess rainfall, the peak of the direct runoff is 455 meter cube per second. But in for unit hydrograph, we have 1 centimeter excess rainfall. So the peak of unit hy unit hydrograph will be 455 by 6.5. So what will be the volume? It's 70 meter cube per second. That's how we calculate. So next what they are saying is the watershed has an area of 2,647 kilometers square. The ordinates of flood hydrographs are given in the table where the direct runoff starts at 3 days. Okay, compute the base flow and direct runoff at time t equal to 3, 5, 7 and 9, 9 and 11 days using straight line method and fixed space method. So here you can see that the discharge versus time values are given in this table. Okay, this we are plotting it. So from the plot, it is clearly visible that it's not direct runoff because these start and end points, it's not touching x-axis anywhere. So it is a flood hydrograph. So first, what we are trying to do is they are trying to come asking us to compute the base flow. First, we will calculate using straight line method. Okay. In straight line method, what we have discussed, we have discussed that we will join this start of the rising limb and end of the recession limb. So here you can see for at about point 105 there is a sharp change in the slope. So we consider this as the end of the recession limb and we will first join line A and D and we will calculate slope of AD. Okay, how do we calculate slope of AD? So we know the ordinates are 140 and 105 meter cube per second. Okay, at A and D respectively. And the time values are 3 days and 11 days at A and D respectively. So using this point is 3 comma 140. This point can be written as 11 comma 105. Between 2 points, we know how to calculate scope y2 minus y1 by x2 minus x1. So it is 140 minus 105 by 11 minus 3. 4.375 meter cube per second per day. You can see the y-axis are in units of meter cube per second and the x-axis is in days. So when you are dividing it, the units will be meter cube per second per day. Right. So and also you can see the slope is negative. It's inclining downwards, right? It's going so it's a negative slope. So when I'm calculating the discharge value for fifth day, how we will calculate is we are joining all these points by a straight line. Okay, sorry. So we are estimating discharge. Sorry, sorry. Now we will calculate for at each time step. We are trying to calculate what will be the base flow value. So since A and D are joined by a straight line and we know the slope, we can calculate the ordinates value at different time periods. Okay. By using the suppose the line is following y equal to mx plus c. So what we will do for will from this point we are trying to calculate the ordinate of this at time equal to 5 days. Alright, so what we will do just 140 minus since the this is 2 days 2 into slope. So that is equal to 131 approximately meter cube per second. And then we have similarly we will calculate what is the base flow at a time equal to 7 days. Now we have to take whatever the value is here, 131 minus 2 into, again 2 days. From 5 to 7, we have 2 days interval. Multiply with slope, 122 meter cube per second. Again at ninth day, what will be the base flow value? Seventh day base flow minus 2 into slope. We'll get 113 around meter cube per second. So then we will calculate 11th day, what will be the base flow. So here you can see at the end of the table, we have given what is the flow discharge value. That is this value. Okay. Value at each time step, that is t equal to 3 days, 5 days, and etc. And by using straight line method, we have calculated the base flow as well. And we are writing it down. And by subtracting uh, second row from first row, we can calculate the direct runoff. Okay. You can see that initially they're always becoming zero because initially what we are considering at this point the base flow is equal to flood hydrograph. And at this point also the base flow is equal to flood hydrograph. So that's why we are getting zero values. Now in case of fixed base method, what we have to do is first we have to calculate the number of days after the peak. That is using 0.827 into A power 0.2. That is 0.827 into what is the area of catchment they have given? 2647 kilometers square. After calculating, we will get it as 4 days. So after 4 days, this is our point. See, day 1 from the peak. Okay. Day 1, 2, 3, and this is our fourth point. Okay. So now what we are doing is we know that we are drawing a vertical line at the peak. Huh? And we will draw a tangent at this point A, and we will see where it is intersecting this vertical line. And how we will calculate the slope of this line? We are drawing a tangent. So this will be our line. So it's passing through point this, and these 2 points it is passing. So slope of AF is equal to, it's passing through 1 comma 200, and also it's passing through 3 comma 140. So just calculate the slope. 200 minus 140 by 3 minus 1. This is equal to 30 meter cube per second per day. And the base flow occurring at 5 days. So it is lying on this line only, right? So what we will do is 140 minus from third day 4, 5. So it is 2 days. Next 2 days into the slope is 30. It's a downward slope, right? So it's negative. We have to subtract. So that is 80 meter cube per second. Similarly, at the F is occurring at day 6. So we need to calculate what is the base flow at day 6. So 140 minus 6 minus, this is 3. Because 140 meter cube per second is occurring at day 3. Okay, and we multiply by slope. So we will get 50 meter cube per second. So now here we know F point is 6 comma 15 and S is I think it's 10 comma 175. So now we will calculate slope of Fs, that is 175 minus 50 by 10 minus 6, 31.25 meter cube per second per day. So get that since day 7 is falling on this Fs line, what we will do, and it's also an increasing slope. So the slope is positive. Here we know it is 6 comma 50. So 50 plus on 7th day. And on 6th day value is 50 into slope is 31.25. So we'll get a value of 26, sorry, 81.25 meter cube per second. The base flow on ninth day is also falling on line FS, right? So what we will do, 81.25 less 9 minus 7 into slope. That is 143.75. And on 11th day, it is 105. So like this, so this area. So on 11th day will be same as point D, whatever the flood hydrograph ordinate will be equal to the baseline. So like this, we have flood hydrograph values, flood discharge values at each time step, and also we calculate base flow values. And once we subtract these two, we'll get the direct runoff hydro. So here we are seeing that the ordinates of 6-hour unit hydrograph are given below. Derive 12-hour unit hydrograph of the same unit volume as that of 6-hour unit hydrograph. Here we see that from 6-hour unit hydrograph to 12-hour unit hydrograph, just by method of superposition you can calculate it. So what we are doing is we have 6-hour unit hydrograph. So that means in 6-hour unit hydrograph, we are seeing 1 centimeter rainfall occurred. And in next 6 hour also, we are saying same 1 centimeter rainfall has occurred. Okay. That means what we will say, if we have a unit hydrograph ordinates, we will just lag the ordinate values by 6 hours. So there won't be any values at 0th hour and 3rd hour. Okay. So this, suppose this is our direct runoff hydrograph for 6 hour duration and 1 centimeter. And at 6th hour, we have to draw one more direct runoff hydrograph. Okay. Or unit hydrograph in this case, which has 1 centimeter excess rainfall. So at on 0th hour, there won't be any value. At 3rd hour, there won't be any value. We lag it by 6 hours. So that the total duration of excess rainfall will be 12 hours. Okay. So we will lag it, and each row we will add this up. So in each row we are summing it up. We are adding up column 2 and column 3 to get the superimposed hydrograph. So like this we will get. But what is happening here? We can see that in 12 hours there is 2 centimeters of rainfall that is occurring. Because since it's at 4 centimeter per hour, sorry, 1 centimeter per hour intensity occurred. Once we calculate this area, it is 1 centimeter per hour into 6 hours, the first block, plus 1 centimeter per hour into 6 hours. Sorry. So here it is 1 centimeter and 1 centimeter, right? So in total 12 hours, if we add it up, it is 2 centimeter of excess rainfall that is occurring. So from principle of proportionality, what we have discussed, if we have uh, for the mm of excess rainfall, if we have a direct runoff hydrograph, we will just divide all the ordinates of direct runoff hydrograph by d centimeters or to get the unit hydrograph. So since here we are obtaining all these ordinates for 2 centimeter excess rainfall, to get for 1 centimeter excess rainfall, we have to divide each ordinate by 2. Okay, so that's how we are getting these values in the last column. And I'll give a quick idea of how to calculate unit hydrograph for different durations. So here, as we have discussed before, suppose we have a unit hydrograph for 4 hour duration. Uh, so 4 hour duration unit hydrograph is available. Okay, what we will do is, and we are trying to calculate for 12 hour. What first we will do is we will use a method of superposition. That is like we will to get 12 hour unit hydrograph, we need three hydrographs, right? So we will have three hydrographs as well, which will be each of them will be lagged by 4 hours each. So this is our first hydrograph, second and third. We can see here. So once we have this, we will add all these up. All the ordinates will be added to get one main hydrograph. That is our 12-hour direct run of hydrograph. But we can see that total excess rainfall that is occurring is here 3A. In this case, it's A. That is generally it's 1 centimeter. That is here 3 centimeter. So each of these ordinates should be divided by 3 to get unit hydrograph for 12-hour duration. So this is only possible when we are trying to develop from D hour unit hydrograph. We are trying to develop ND hour unit hydrograph where N is an integer. Only in this case we can uh, use method of superposition. But if the n value is not an integer or a fraction, if it is a fraction, then what we can do is we have to go with a method called S-curve. So in case of S-curve, what we are trying to do is if we have a unit hydrograph for d hour duration, okay, first we'll plot that and we will do an infinite additions by lagging the unit hydrograph with d hour. So suppose this is our unit hydrograph for d hour. We will lag it by d hour. Then we will plot one more hydrograph. Again we'll lag by d hour. One more hydrograph. Like this we will lag infinite times. Okay. And then overall we will have a one single hydrograph. That is called as S-curve. Okay. This this discharge, which will become constant after some time, is called as equilibrium discharge QE, which can be calculated using this formula 2.78 A by D, where A is the catchment area in kilometer square and D is the duration of the unit hydrograph in hours. Okay. So once we get the S curve, what we are trying to do is, if we want for any T hour duration, okay, suppose from D hour unit hydrograph, we need a T hour unit hydrograph. Okay. What we will do is, we have an S curve and we will just lag this S curve by T hours. And draw one more S curve. This suppose we call this as SB. Then by subtracting SB minus SA, this will give us a direct runoff hydrograph due to T hour duration, excess rainfall with magnitude T by D centimeters. Okay. So already we know that if it is T by D centimeter excess rainfall, how we will get unit hydrograph? We will just divide SA minus SB ordinates by T by D. Then we will get T hour unit hydrograph ordinates. Okay, I hope this is clear. Is there any questions related to how to calculate and suppose T hour unit hydrograph from D hour unit hydrograph when the relationship is T equal to ND? and n is integer, we will use super method of superposition. If n is an integer, we will use S-curve method. Any questions? So the last two problems, what we are trying to do is we have the catchment area of 360 kilometers square, and for 6 hour duration unit hydrograph, they are asking us to calculate equilibrium discharge. So we know QE is equal to 2.78 into A by D. So it is 2.78 into A is area of catchment 360 kilometers square by T is 6 hours. So once you calculate this, you get around the equilibrium discharge value as 167 meter cube per second. Okay, now the next question is that asking us to derive S-curve ordinates from a given unit hydrograph. So suppose this is our unit hydrograph, then what we will do is we will have an infinite addition of this unit hydrograph we have to do by lagging it uh, by 4 hours at each time, at each in each case. So instead of that, we have a simple S-curve addition method where we will do in this is, so first we have these are the ordinates of 4 hour unit hydrograph. In S-curve addition, what we are doing is in the previous row, we'll add with the previous row of ordinate of 4 hour unit hydrographs. Okay, then we will get the current ordinate of S-curve addition. So like this, 0 plus 10 will get the next ordinate of S-curve addition. Like this, we will have 10 plus 30, 40. 40 plus 25 will have the next row. Like this, once we get S-curve addition, what we will do is we will just add up the second and third column. Unit ordinate of 4 hour unit hydrograph with S-curve addition. We'll both add these two to get the S-curve ordinates. So 0 plus 0, 10 plus 0 is 10, and 30 plus 10 is 40. So like this, for each row we will do to calculate the S-curve ordinates. Why we are not going with the huge method where we will lag this unit hydrograph by 4 hours and we will get infinite columns. Suppose here we have 28 values, right? So 28 by 4, since it's 4 hour duration unit hydrograph, 7. So we need to use minimum of 7 unit hydrograph to have a S-curve. So we will have 7 columns. Each will be lagged, like first column will be lagged by 4 hours, second one is 8 hours, 12 hours, like that. So it will be like a huge calculation procedure. So instead of that, we will go with S-curve addition method directly to get S-curve ordinates. So this is how we'll get S-curve, and by subtracting two S-curves, we'll get an unit hydrograph for P-hour durations, like I have told before. Is there any questions related to this topic? How we will construct unit hydrograph and how from D hour duration unit hydrograph we can get ND hour unit hydrograph, and from unit hydrograph how we are calibrating flood hydrographs, and also vice versa. Is there any questions related to these topics? If there are no questions, we can end this session. Thank you for attending.